All right, and finally, Sabry will tell us how to bake a quantum pie. Off you go.
Okay, so quantum computing is quite an interesting thing, and it's a big mystery in some sense. I mean, we know quantum mechanics, quantum physics exist, and all of the stuff that this computer would not exist without some quantum effects. But trying to exploit quantum effects to write programs and hopefully speed programs is not very well understood. So we have been doing work, and this have been like in a series of papers with my collaborators here, Robin and Chris and Jacques, on trying to explain quantum computing from starting from classical kind of developments. We don't want to reinvent completely new things. Classical computing is well developed, and there are lots of ideas. All of these effects and monads and arrows are actually enough in some sense to explain what quantum computing. So I'm going to try to explain to you how to understand quantum computing from just basic notions of effects and classical programs we know. Okay, so the basic idea is going to be the following. We're going to have a classical language, and we're going to have two different interpretations of the classical language. So there will be the ones on the left and right, and there will be some glue, and the glue is special, that will combine all of that to make a quantum language. So if you understand the classical languages and understand the glue, you get your quantum language. Okay, so let's be specific. So let's start with just the most basic data type that we have, Booleans. So we have false, true, blah, 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 and we're going to interpret them using vectors. So this is because we're going to try to lead to quantum computing. So false is going to be a vector 1, 0, true is going to be the vector 0, 1, and then you can play a little game and kind of do not and do various kind of operations, and they're all vectors and matrices. The details are not too important, but the point is you have Booleans interpreted using vectors and matrices, completely standard. Now we can have a different interpretation. So there's no reason to pick specific vectors. I mean, this is a choice. As long as you maintain the semantics of the operations, you can do anything you want. So what we are going to do instead is we're going to rotate those vectors, conjugate the classical interpretation that we've seen in the previous interpretation. So we're going to rotate, do the usual vector, rotate again. And we're going to pick, specific rotation to kind of make a point that if you pick this rotation that has pi over 8 angles, then the not operation, which is the matrix 0, 1, 1, 0, becomes that matrix 1, 1, 1, minus 1. And that matrix is a very special matrix, and it's called the Hadamard matrix. The reason this is special is because there's a result that says that quantum computing is nothing but a Toffoli gate and a Hadamard gate. What is Toffoli? Toffoli is just Boolean conditionals, and Hadamard is what we have seen. So this is a well-established result, and it tells you that, in some sense, the only thing you need to do quantum computing beyond classical computing is to have this kind of rotation operation. So this is one node. So what are we doing now? What we're trying to do is we're trying to take that result and allow you to reason about a quantum language by composing, just in the spirit of the previous talks, is you take a classical language, it has an equational theory, you take another classical language, it has a slightly different equational theory, and then you combine all of that to reason about the quantum language. And we're going to build that using the ingredients we have seen. So this is kind of the game. It's going to take what is in some sense well-known in, well, if you live in that area, and we're going to try to reason in a modular way about the quantum language by composing reasoning principles for a classical language. So this is where we're going. We don't read it now. But this is kind of where we're going, is we're going to, in Agda is completely classical in some sense, right? And we're going to embed the classical theories inside Agda and be able to reason and prove things about quantum programs by composing classical reasoning as we have seen. Okay, so what is the starting point? So I said the starting point is a classical programming language. Classical programming languages are not typically reversible, but there's no reason why they shouldn't be. It's completely kind of an arbitrary choice that we chose, like lambda calculus or Turing machines. If you read back the history of computer science, the choices of the abstractions we chose in the 1930s were arbitrary. We could have chosen different abstractions to make the languages reversible. So if you choose a classical reversible language, this is one, I mean, this is like it's like a calculus, if you want. It's not the real language. It's the core language. And the core language is based on isomorphisms between types. So you can look at all of this as the usual type isomorphisms you have in Haskell or ML or Coq or whatever. So you have isomorphisms between, times is associative and it's a monoid, and you have distributivity of, products over sums and usual type isomorphisms. And this could be a core language for classical reasoning. And you can actually use it to program. So it's a complete language if you are in the world of finite types, which is typically what quantum programming is. You don't go to, recursion and loops and whatever in quantum are kind of problematic. It's like open kind of research problems. But you can use it to program. You can write lots of interesting programs in that. And it has a well-developed classical theory. So this is, again, well known from Laplace, like coherence for monoidal categories. There is sound and complete reasoning principles for these theories, which were developed a long time ago. So you have a classical language that is well developed with a classical theory, equational theory for it. So now what we're going to do is we're going to play this game of giving different semantics of this classical language. So we're going to start by giving one semantics in a category of vector space, which is what I mentioned, everything is a vector and the operations are matrices. So this is the category of unitary Hilbert spaces and unitary transformations. Big words, but the point is every type is a vector space of some kind, and the programs are maps between those vector spaces that obey certain conditions. And then this category is a monoidal category. It has a product and a sum that are monoids, essentially. And then we have another category, which is also some kind of unitary operations, but they're all rotated. So we take the previous interpretation and rotate. So these are two different categories, interpreting the classical language. And so far, we have two classical languages with different interpretations. We're going to build, again, using a known construction, which is the amalgamation of categories. So there is a construction that takes two categories and amalgamates them. And what amalgamation does intuitively is it allows you to take a morphism from here, one from here, and iterate. So you build a morphism in the new category by composing morphisms and alternating. So you take a program from here, one from here, one from here, from here. So now the independent classical languages that never interacted now can be interleaved. So I take a program from this language, one from that language, and interleave. And while I'm doing this, I'm going to maintain that they have different the monoidal sums are not kind of squished. They are kind of maintained independently, but the products are squished. There's a technical reason for that in the paper, but we are maintaining different sums and unifying the products as we're doing this construction. Then this is where the arrows and effects kind of show up very clearly. I mean, the paper is all arrows, the Hughes arrows like we talked about last time. Here, what we're doing using the arrows for is to hide information. So programs are going to be allowed to hide part of the input and hide part of the output. So that allows you to build programs that are not isomorphisms. I mean, they are isomorphisms in the kind of the background, but you're hiding some information in the input and output, so it appears that the programs are taking A to B, where A and B are not equal. Okay? So you get certain programs you can write now that go from 1 to 2, from 2 to 1, whatever. So you can write kind of more interesting programs. And this will be used for initialization and measurement of quantum effects. Okay. So this is the punchline, if you want, of like these equations. This kind of, I said we have a classical language, another classical language, and in between we have this amalgamation. When you work everything out, the amalgamation requires you to have these equations. So whatever these equations mean, you need to look at the details. But these equations are kind of boring. They are telling you that you can just classical, if you copy, you can kind of, the two copies are indistinguishable, nothing interesting. This one is very, very interesting, and this is an algebraic formulation of complementarity. Goes back to Bohr, quantum mechanics, 1930 or 20, whatever, which is the defining, at least arguably at the time, the defining characteristic of quantum mechanics as opposed to classical mechanics. So this is an algebraic formulation of it. It's not due to me, or it's kind of done before us. And then the main result is there's a theorem that says this is quantum. So let me show you now how, how can you use all of this? Forget all of the semantics, all of the category theory, all of this stuff, is you can have this language, which is the user-facing quantum language. There's nothing quantum here in terms of there's no complex numbers, there's no matrices, there's nothing. There's two errors, one that lifts standard interpretation of Booleans, another one that lifts the rotated interpretations, the one with the phi. There's one monoidal product, which is mult. And then there's the composition for category ID and composition, which is the error things. And then there is the effects 0 and assert 0, which are the hide information and create information. So this is the user-facing language. You can write your typical quantum circuits in that language. You can reason about them, and you can prove things about these languages. Again, you know nothing about quantum. All you know is previously developed monoidal categories and coherence conditions, plus the two new equations we have, and you can write and reason about these programs. So have we learned anything useful for physicists? Maybe. Do we know any reason why quantum computing could be faster than classical computing? Again, I have no idea. Is it potentially something that will help us kind of understand all of these questions or improve our ability to write and reason about quantum programs? That's the hope. Well, lots of other ideas on how to pursue all of this. And I guess these are best left for questions or discussions. If you need anything, I'll be around and happy to talk about any of this. Thank you. Yeah, I can rely on you to give a question. Be nice.
Hi, Dominic Orchard. This is really lovely. So is there a story of how measurement can fit in here, right?
Oh, yeah.
That kind of causes some kind of effect or something.
Yeah, so I didn't mention it in this talk, but in the paper, there's one more arrow you add on top of all of that to do measurements, yes. And that's an old paper by Robin and Chris that we kind of tacked on this one. But yes, it's another arrow on top of all of that.
Okay, another arrow that sort of embeds into this thing. But does it have some kind of, it's like an effect that leaks out, right? So it sort of has some...
So it's just like the state effect that we have here, but it's kind of like a... yeah, I mean this one is not supposed to be observable because that's the initialization, but the other one is like the I/O kind of version of the effect. But yes, it's kind of similar idea, one more arrow, and it's the I/O version that is global, kind of on top of everything.
Okay, cool. Thank you.
So thank you for liberating quantum programming from low-level Hilbert space stuff. I wanted to know if, in exploring this stuff, you found anything that can be brought back to traditional programming. Like, did you learn things that could affect how you write non-quantum programs? For example, your fractional and negative type stuff.
Yeah. So yeah, so the goal, I mean, so kind of like my dream, like, I don't know, like 10 years ago or whatever, 20 years ago, was to learn from physics, like change classical programming to be inspired by physics, and vice versa, kind of like teach, the physicist that, we have some cool stuff that you can use, and they need to use abstractions and forget matrices, and matrices are kind of like useless. There are lots of kind of, I mean, so yes, we have lots of ideas, but none of them has been realized like at a full scale yet, but we're exploring various ways where, inspired by the way quantum physics composes things and parallelizes things, and we're trying to kind of develop classical languages that would benefit from this. I think it's promising. I think it's like, if you want to think about how to compose massive parallel computations, that's probably the way to do it. I mean, in physics, this happens all the time, or in nature or biology, whatever. And trying to program that way would be like a very nice. So anyway, maybe the next paper or next few papers we'll pursue this more, but thank you, yes.